досить. Хорошо. Almost positive Tits, quadratic forms, join with Marina Stepachkina. Yes. Так. The report is devoted to the Tits quadratic forms, integer quadratic forms of a special type, playing an important role in the modern representation theory. It reviews some results received over the past 18 years by me together with Marina Stepachkina, including this year's results. The using of my minimax isomorphism method allows us to perform quite complex calculations without computer programs and deeper understand the essence of the emerging statement. If briefly, let S be a finite poset, A be its minimal or maximal element, and T is equal as row A, denotes the following new poset. T is equal as usual sets, T minus A is equal S minus S as posets. The elements are in T is already respectively maximal of minimal, that is vice versa, and A is comparable with another elements in the new poset if and only if they are incomparable in S. Comparable in T if and only if incomparable in S. In the language of Hasse diagrams, such simple translation S to T can be viewed as an image in a kind of crooked mirror. A poset S is called minimax isomorphic to a poset. A poset S over linear S is called minimax isomorphic to a poset S if it is isomorphic to some poset which is obtained from S by successively applying a finite number of such operations. For example, the poset T1 and T2 of the form are respectively minimax isomorphism to the poset S1 and S2 of the form. In the left case, we must take points 3 and 4, and in the right case, we must take points 1, 2, and 3. In the first, the main motivation for introducing this notion is the fact that the Tits quadratic form of minimax isomorphic posets are Z equivalent. The poset from the 8th point generates a minimax isomorphic class from 50 posets, proving the Z equivalence of the corresponding 50 Tits quadratic form by the methods of classical linear algebra is a very complex and laborious task. The Tits quadratic form of quivers and posets. All quivers and posets are assumed to be finite. Let Q be a quiver with a set of vertices Q0 and the set of rows Q1. If one takes all matrix representation of a field K of any fixed vector dimension Z, Then comes the number of parameters of all matrices and the number of parameters of the matrix group acting on these representations. And finally, subtract the first number from the second, we will get the quadratic form, which Gabriel called the Tits quadratic form of the quiver Q. Theorem 1. Let Q be a connected quiver and K a field. Then Q is of finite representation type over K, that is, has up to equivalence only finitely number in the composable representations, if and only if the following equivalent condition hold. First, the Tits quadratic form is positive. Second, Q is a Dynkin quiver. That is, the corresponding undirected graph is a simplified Dynkin diagram. Now consider the case of posets. Let S be a poset with a order relation preg. Without loss of generality, we assume that S is equal to 1 to n. In addition, we identify posets with the Hasse diagrams. Recall that a matrix representation R over a field K of the poset S is, by definition of Nazarova and Reuter, a block matrix M with size Z0 is the number of rows, and Z1 plus Zn is the number of columns, on whose rows acts the full matrix group, and columns the group of all block matrices consistent with the partial order. More detail, an ij block is equal to 0 for any I greater than j. The calculation of the number of the parameters show that the Tits quadratic form of the poset S is equal to Theorem 2. A poset S is of finite representation type if and only if the following equivalent conditions hold. A. Drozd condition. The Tits quadratic form is weakly positive. That is positive on the set of vectors with non-negative coordinates. B. Kleiner's conditions. S does not contain full subposet of the form. We call K1, K5 the Kleiner's poset, and the equivalence of the conditions A and B Drozd-Kleiner theorem. Note that the Tits quadratic form of a quiver is weakly positive if and only if it is positive, but it may not be for a poset. Therefore, new natural problems appear for posets, and first of all, on an analog of Drozd-Kleiner theorem for the Tits quadratic form to be positive. We call a poset positive, weakly positive, etc. if respectively so is its Tits quadratic form. Then the Kleiner's posets form a complete system of posets that are not themselves weakly positive, but all their proper subposet already are. Such posets we call WP critical. If one introduces the notion of P-critical poset that is critical with respect to positivity in a similar way, then WP critical posets are also P-critical because their proper subposets are positive. But there are much more critical ones, namely 75 up to isomorphism and duality. The table of critical posits, 75, positive posits. Since the positive posits are analogs of Dynkin diagrams, then the problem of the description is also important. A positive posit S can be serial when exists an infinite sequence of positive posits that start with start with it, and non-serial if otherwise. We proved the following theorem. A poset S is serial positive if and only if it has one of the following forms, 3 type, where the vertical lines are chains, some of which may be empty, and the inclined segments do not contain intermediate points. Theorem 4, any positive poset of order n greater than 7 is serial. Theorem 5, there are up to isomorphism and duality 108 positive non-serial posits. 108 almost positive posits, new results. A non-negative poset S, that is the Tits quadratic form, accepts only non-negative values. So a non-negative poset S that is not positive is said to be almost positive if there exists an element X such that S minus X is positive. A special case of such posets are pi-critical bonds. We have the next theorem. A poset S is serial or almost positive if and only if serial, if and only if it has one of the following form. Here, the larger points indicated in the pictures must always be present. Otherwise, we may have positive posets of isomorphic posets. Theorem 7, any almost positive poset of order n greater than 8 is serial. Theorem 8, there are 322 up to isomorphism and duality non-serial almost positive posets, non-serial almost positive poset. Among them, 75 pi-critical and 147 others, which are indicated in the following non-edited tables. sorry, non-edited. 100, 247, non-edited. Go the 6, 7, and 9, and 8. Other, order cannot be. Sorry. From the above calculations, at some additional consideration, it follows that any non-negative poset which is not positive and serial is minimax isomorphic to a poset that has infinitely many equivalency classes of exact indecomposable representations over arbitrary fields. Thank you. Thank you very much.
Thank you very much for your talks.